In this video, I am going to discuss about the Laplace transformation. If a function will be given, how to find the Laplace transformation of that function. So before going to the thing, let me start with the definition of the Laplace transformation. Let f of t is a function of t defined for defined for all t is greater than or equal to 0. Then Laplace transformation Laplace transformation of f of t is defined as Laplace transformation of f of t, and that is nothing but integration 0 to infinity f of t e to the power minus st dt, and generally we denote it as fs. Okay, so Laplace transformation of small f of t is equal to capital F of s. So that variable t is transformed to the variable s, and Laplace transformation is nothing but it is an improper integral. It is an improper integral. If this integral exists, we denote it as f of s, and sometimes we can denote it as like this also, f bar of s, or we can denote it as sometimes phi of s. So if this integration exists, then we say it is the Laplace transformation of the function f of t. So similarly, we will have the inverse Laplace transformation if we have the Laplace transformation. So inverse Laplace transformation. Inverse Laplace transformation. If Laplace transformation of the function f of t is fs, then the inverse Laplace transformation, the inverse Laplace transformation of f of s is given by is given by L inverse of f of s, and that will give you the original function f of t. So if you are taking the Laplace transformation of f of t, we will get fs. But if we take inverse of fs, we will get the original function f of t. Now let us discuss about some Laplace transformation of some standard function. So Laplace transformation of some standard function, which will be useful for proceeding topics, standard functions. So let me start with first is, say let f of t equal to 1. F of t equal to 1. Then what will be Laplace transformation of f of t, and that is equivalent to Laplace transformation of 1. And according to the definition of Laplace transformation here, Laplace transformation of a function is nothing but integration 0 to infinity f of t e to the power st dt. And so accordingly here f of t is 1. So my integration will be 0 to infinity e to the power minus st dt. So if we integrate it with respect to t, s will be a constant. S will be a constant, and integration of e to the power minus st is nothing but minus 1 by s e to the power minus st. And let us put the limit from 0 to infinity. Let us put the limit from 0 to infinity. So if you put the upper and lower limit, we will get minus 1 by s, and then upper limit will be e to the power minus infinity minus e to the power 0. And so finally we will get 1 by s. So Laplace transformation of 1 will be nothing but will be nothing but Laplace transformation of 1 will be nothing but 1 by s. Similarly, suppose I will take f of t is nothing but k. So in place of 1, I will take k. Then Laplace transformation of f of t, which is equivalent to Laplace transform, which is equivalent to Laplace transformation of k. Laplace transformation of k, and we will get it as k by s. So in place of k, if I take any constant 1, 2, 3, minus 1, minus 2, minus 3, and so on, so I will get the Laplace transformation as like this, k by s. Now, suppose I will take f of t. F of t is equal to t. So I will take only, it is a variable t. Then what I will say? Laplace transformation of f of t is equal to Laplace transformation of t. And according to the definition, this is nothing but integration 0 to infinity t e to the power minus st into dt into dt. And so if we integrate this one by parts, what will happen? T will be the first function, e to the power minus s will be the second function. So what will happen? We will get first function into integration of second function is minus 1 by s e to the power minus st minus integration 0 to infinity. So this integration will have integral limit as 0 to infinity, and integration derivative of first function is 1. Integration of second function already we found here 1 by s into e to the power minus st dt. And if we simplify it, we will get it. If I put e to the power minus infinity, which is 0, if I put t equal to 0, 0 into something will be 0. So the first part is going to be 0. And then the second part, minus is already there inside the integral. So minus and this minus will be plus. Plus 1 by s is independent of t, so we can take it out. And the remaining thing will be e to the power minus st dt. Okay, and so what will be the thing happen here? 1 by s integration of e to the power minus 1 by s is again minus 1 by s e to the power minus st, and the limits are 0 to infinity. And the limits are 0 to infinity. And finally, if we simplify it, we will get we will get 1 by s square, 1 by s square. And so we can write it as 1 factorial divided by s to the power 1 plus 1. That means when I am taking Laplace transformation of t to the power 1, I am getting 1 factorial divided by s to the power 1 plus 1. Similarly, when I will take f of t is equal to t square, then Laplace transformation of t square will be nothing but 2 factorial divided by s to the power 2 plus 1. Okay, and so on. So if I take Laplace transformation of t to the power n, then we will get n factorial divided by s to the power n plus 1. So this is the formula to find the Laplace transformation of a function f of t equal to t to the power n. If n equal to 1, we will have 1 factorial by s to the power 1 plus 1. N equal to 2, 2 factorial by s to the power 2 plus 1. And 3 means 3 factorial divided by s to the power n plus means 3 plus 1. Okay. So in the other way, what will be the inverse of this? Suppose if I have Laplace transformation of t is nothing but 1 by s square, then inverse Laplace transformation of 1 by s square will be nothing but t. Will be nothing but t. Similarly, inverse Laplace transformation of 2 by s cube will be nothing but t square. So Laplace transformation of t square will be 2 by s cube. Then Laplace inverse of 2 by s cube will be t square, and so on. So okay. So this is one type of standard function. And next, third function is, suppose I will take f of t equal to e to the power at, or you can say e to the power minus at, depending upon the situation. If I take exponential function, then when I take Laplace transformation of f of t, that is equivalent to saying Laplace transformation of e of at. E of at means, according to the definition, it is nothing but integration 0 to infinity e of at into e of minus st and dt. So that means this will be equal to integration 0 to infinity, and we will have e to the power minus s minus a of t dt. So when we will integrate it with respect to t, s minus a will be constant, and so integration of this one will be minus 1 by s minus a, and integration of that one will be nothing but, so integration of this one will be e to the power minus s minus a into t, and the integration limits are 0 to infinity. So if you simplify it, then what we will get here is, finally we will get minus 1 by s minus a, and e to the power minus infinity minus e to the power minus 0, and so finally we will get 1 by s minus a, 1 by s minus a. So Laplace transformation of et, e to the power at equal to s minus a. So suppose I will take e to the power minus at, then the Laplace transformation of this one will be nothing but 1 by s plus a. So if I am taking plus here, it will be 1 by s minus a. If I am taking minus a here, minus e to the power minus at, I will have s plus a here. Similarly, what will be the inverse? If I find inverse of 1 by s minus a, I should get it e to the power at. And similarly, inverse of 1 by s plus a will be nothing but e to the power minus 80. So like this, we can find the inverse and the corresponding Laplace transformation and its inverse Laplace transformation. Suppose I will take another standard function, say f of t equal to I will take sine 80. F of t equal to, suppose, sine 80. Now, okay, sine bt I will take, sine bt. Now if I take Laplace transformation of sine bt, then that is equivalent to integration 0 to infinity e to the power minus st into, or you can say it is 80 only, so that it will be clear, it into sine 80 dt, sin 80 dt. Now here I will give you one formula, then I will apply that formula here, and I will tell you the thing. So formula is integration e to the power 80 into sin bt dt will be e to the power 80 divided by a square plus b square. If we do by parts integration, we will get it into a sin bt minus minus b cos bt, b cos pt, and whatever limit will be there, we will put that limit here, and that will give you the thing. So this is the formula I will apply here. This is the formula I will apply here. So in place of a, I am having minus s. In place of b, I am having a. So what I will do here is e to the power minus st divided by a square means s square. So s square plus a square whole into, and here a is nothing but minus s. So minus s sine 80, and b means a, minus a cos b is nothing but a, 80, and then I will put the whole limit as 0 to infinity, because my integration limits are 0 to infinity. So if I put to the integration infinity, e to the power minus infinity will be 0. So first thing will be 0, and second thing will be t equal to 0. T equal to 0 means e to the power. So I will have minus e to the power minus 0 divided by a square plus a square into sine 0 is 0. So I will have cos 0 is 1 minus a. And so finally I will have a by s square plus a square. That means Laplace transformation of sine at will be nothing but a by s square plus a square. Okay, then the inverse of this, L inverse of a by s square plus a square will be nothing but sine of 80, sine of 80. So similarly, if I take f of t is cos 80, then Laplace transformation of cos 80 will be nothing but s by s square plus a square. Okay, so and inverse of this will be nothing but s square, a square will be nothing but cos 80. Okay, so when I am having the Laplace transformation of sin 80, the numerator is a, but when I am having Laplace transformation of cos 80, the numerator is s. So that is the difference between Laplace transformation of sine and cos. Now I will take another standard function, say my f of t equal to sine hyperbolic 80. You know, sine hyperbolic 80 is e to the power 80. Sine hyperbolic 80 is e to the power 80 minus e to the power minus 80 by 2. So now you know Laplace transformation of sine hyperbolic 80 will be nothing but constant is there 1 by 2, then Laplace transformation of e to the power 80 minus e to the power minus 80. So from the linear property of Laplace transformation, we can have it as 1 by 2 into Laplace transformation of e to the power t minus Laplace transformation of e to the power minus 80. Okay, and if you find this thing and simplify it, so this will be 1 by 2, and Laplace transformation of it to 1 minus s, 1 by s minus a minus 1 by s plus a. So if you simplify this, we will get it as a by s square minus a square. So this is the Laplace transformation of sine hyperbolic 80. So what is the difference between sine 80 and sine hyperbolic 80? In the case of sine 80, a square plus a square in the denominator. But in case of hyperbolic 80, we will have a square minus a square. And the same thing happened to sine also, cos also. Laplace transformation of cos hyperbolic 80 will be nothing but s by s square minus a square. So if it is the thing, inverse of a by s square minus a square will be nothing but sine hyperbolic at, and in this case inverse of s by s square minus a square will be nothing but cos hyperbolic 80. Cos hyperbolic 80. So like this we can able to find the Laplace transformation of some standard functions. Now here I can say some property, but that property we will discuss in the next thing. But here I want to say one basic thing, that is maybe called as shifting property. So another thing I will say here, next six standard function. Suppose I have f of t equal to f of t, or you can say g of t equal to e to the power at into f of t. Then Laplace transformation of g of t is equal to Laplace transformation of e to the power at into ft. Okay, so when you are having the function multiplied with e to the power at, that time what you do, you first find Laplace transformation of f of t, and then after getting the Laplace transformation of f of t, wherever s will be there, you replace it by s plus a. You replace it by, sorry, s minus a. If it is plus, you write here s minus a. If it is e to the power minus at, you replace it by s plus a. Okay, and so that will be nothing but f of s minus a. That will be nothing but f of s minus a. So in place of s, you will have s minus a. That, for example, if I say Laplace transformation of e to the power 2t into t, then what I will do, I will find Laplace transformation of t, then wherever s will be there, I will replace it by s minus 2. I will replace it by s minus 2. And then what I will get here? That will be nothing but Laplace transformation of t is 1 by s square, and then wherever s is there, I will replace that s by s minus 2. So finally I will get 1 by s minus 2 whole square. So when I will find inverse of this, so for such function, L inverse of 1 by s minus 2 whole square, then what will happen? For the s minus 2, I will preserve e to the power 2t, and for the remaining thing, I will take inverse. And the remaining thing I will take inverse. And finally, inverse of 1 by s square is t, and so I will get t into e to the power 2. Similarly, if I have Laplace transformation, another thing I am giving, that is a derivative of Laplace transformation. If I say g of t, say 7, g of t equal to t into f of t, into f of t. Then what we will do, how to find the Laplace transformation of g of t? How to find the Laplace transformation of g of t is, Laplace transformation of g of t is equivalent to Laplace transformation of t into f of t. So for the t, you preserve minus d by ds, and then find Laplace transformation of f of t. So for the single t, you find minus d by ds, and then find the Laplace transformation of f of t, differentiate it with respect to s. Differentiate it with respect to s, and that will give you the that will give you what is called the Laplace transformation of t into ft. t into ft. Okay, so like this we can find the thing. Suppose I will take an example here. Suppose I take, say, g of t equal to t into you can say e to the power at. Okay, so I want to use this property. So when I find Laplace transformation of t into e to the power at, what will happen? For that t, I will preserve minus d by ds, and then I will find Laplace transformation of e to the power at. And Laplace transformation of e to the power at is known to us. So minus d by ds of e to the power at is s minus a. Now find the derivative of this one using the thing. If you simplify it, you will get it as 1 by s minus a whole square. 1 by s minus a whole square. So like that, we can find the Laplace transformation if the function is multiplied by t. Similarly, if it is multiplied by t to the power n, that means if g of t is equal to t to the power n into f of t, then Laplace transformation of g of t will be nothing but Laplace transformation of t to the power n f of t, and that means for the t to the power n, what I will do, minus 1 to the power n dn by dsn, and then I will find Laplace transformation of f of t. So I will find Laplace transformation of f of t, and I will differentiate it with respect to s n times. With respect to s n times. Then that will be the Laplace transformation of t to the power n into f of t. Then I will take another type of function. Say I will have like this, in place of s, t. Suppose in place of t, I am having g of t equal to f of at. That means I have a into t. In that case, what will happen? I will have a Laplace transformation of g of t, and that is equivalent to saying Laplace transformation of f of at. Then I will have this one is equal to 1 by a f of s by a. So this may be called as change of scale property. Change of scale property. Okay. So using this standard Laplace transformation, we can able to solve certain problems.